Okay, so we're ready to get started on Module 6, which is going to be looking at force analysis of structures and machines. As we look here, you're going to see kind of the normal components that we see in all of our modules. First, we're going to have a learning plan. As we click on the learning plan, we are going to be referencing a handout. I'm kind of impartial to my old book that I used to use, and this is out of there. It's no longer published. Unfortunately, I can't specify it for you guys. So I do have access to some of the chapters, and some of them are really good. So these are the ones that I've been using as the handouts. So chapter 6 here, or module 6, will be chapter 6 out of the handout, not out of the McGraw-Hill. Okay. So the references that we do here, I have mine printed out, but the PDF is here for you to reference. We already talked about the MD Solid software. So this is the download file and the registration code when you go in. Username is just going to be your initials. You can just, make it whatever you want it to be. And I don't believe there's going to be, if I remember correctly, it's not like you have to put a username and password in each time you do it. It's just for the first time that you install it or set it up, and then you'll be ready to go to use. There are 2 guided notes here. We're going to be doing the first one tonight. This is on trusses, and then the second one is going to be on frames and machines. And then these are the practice problems that we're going to be doing, and those are part of the guided notes. So if you grabbed copies of the guided notes, then you can just follow along and fill in as we go. And then the things that you're going to be submitting are going to be the practice problems and the application problems, just like we've done for other modules. Next in our module is session recordings. I am recording the sessions that we're doing tonight. As you know, these will be uploaded at the end of the evening. But if you look in there and you wanted to peek ahead, I always have the recordings from the previous year uploaded as well. So feel free to explore that if you need to. Practice problems are going to be here. So once we get done with our guided notes for both of those sections, this will be where you upload those. I want to talk about uploads because, and I did start talking about this the last time, but a reminder, as we're getting into like the guided notes or even problems that are multiple pages long, a couple things, it's getting harder for me to do and correct like JPEGs or PNG files, like just the camera files. For a couple of reasons. If they're going in individually, I'm certain you're probably taking them in order, but I think Canvas is mixing them up. So sometimes, I've got them in all different orders. And if you continue to a second page, unfortunately, if you don't label it, I don't know what that's for. Okay. And then I've got to try to go through, and it just takes a really long time. So what I am going to require going forward, I really am not going to do, I don't want you to upload the individual files anymore. Okay. It's my understanding from other classes, they have you download what is it called? Cam Scanner, right? So is everybody familiar with using Cam Scanner? Could you please use that for my submissions as well? Those who've been using Cam Scanner, it works wonderful. And then it's a continuous document for me, so that then it's in the order that you actually take the pictures, and then you've got one file that you're uploading rather than all the different pictures. So please experiment with using that. There are other ways to achieve that. There's other apps. I use Tiny Scanner on mine, but I'm finding that the Cam Scanner takes really nice pictures, and it's nice and clear. So please try to use that as an option if you at all can going forward. Don't worry about anything that you submitted previous to this. Okay. I'll let you know if I have problems. There have been some where there's been like over 20 uploads, and then it's like, I just can't like make head over tails of it, but that's okay. We work through that. Don't redo anything that you have submitted. Just going forward, let's use that Cam Scanner. Okay. So anyway, so that's there. And then your application problems, these are going to kind of go along with the items that we do in our practice problems. So you'll notice here that I have them listed. These are going to come out of the chapter 6 handout, not the McGraw-Hill book. Okay. So these are references to the pages, and I did attach the PDF directly above here with the answers. So I think we're ready to get started. Let me go back one level. So again, if you wanted to follow along in the, I'm going to say quote in the chapter, here's the PDF for that. I have it underneath my camera right here. And don't worry about MD solids right now. We're really not going to demonstrate that till the end of after we've gone through some things here. And you'll get plenty of time to download and play with that when you need to. So what I'm going to do is I'm going to start underneath our camera with the first page of our guided notes. Okay. So our guided notes are here. This is page 1, and we're going to be referencing the handout, which is that PDF that I have attached in the chapter. So at the beginning here, chapter 6 is all about analysis of structures and machines. So I've got some fill in the blanks here. Certainly can read through this section, but we'll add the blanks or the fill in the blanks that we need. So as we look, it says a blank consists of a series of connected structural members or rigid bodies that are designed to blank loads or forces. So in this first one, this is going to be a truss consists of a series of connected structural members or rigid bodies that are designed to support loads or forces. Okay, trusses. Machines, on the other hand, are designed to transmit loads and forces rather than to support them. Okay. Now the other item that's going to support, you can put trusses and frames. So actually it should be both of them. Trusses and frames are going to support loads and forces, and machines are going to transmit loads. So we're going to be looking at all three in module 6, starting with trusses this evening. Okay. In this module, we will be looking at trusses. Oopsie. Frames, and machines. Okay. Now, as we look at the beginning of the chapter here on page 101, figure 6.1 shows us an example of each one of these, types of structures. So the first one here is going to be our truss. We'll talk about examples of trusses, but I'm sure you've seen them. Bridges are a classic example and an application of a truss. Building supports are going to be a classic example. The next one that we have here is a frame. Okay. Frame, again, is going to be very similar to a truss. We're going to find out there are some distinct differences, but a frame doesn't move. It supports forces. The last two that we have down here, these are considered machines. Machines are going to transmit loads and in some cases provide a mechanical advantage. Okay. Through your physics classes, you have already experienced, and I'm sure done, experiments with different types of machines where you transmitted and then also gained mechanical advantage. So we're going to see additional examples of that. So here in module 6, we're going to be looking at all three: trusses, frames, and machines. Okay. So now as we look at our next section here, it's called simple plane trusses. So in statics, we are going to be dealing with trusses that are just in a single plane, meaning we're not worried about that three-dimensional, view. We're looking at just the X and the Y planes. Now, it says here the primary purposes of a truss are going to be to distribute an applied load and to span greater distances. That's why trusses are used for bridges. It's kind of a natural because we can take that load, we can distribute it over a longer length by using different types of truss arrangements. Now, it says up here that a truss is a structure that usually consists of straight uniform bars and members arranged in a series of adjoining triangles fastened together at the ends to form joints. And those ends are going to be pin connections. So, and as we know about pin connections, that means that we have an opportunity for two directions of support. We're going to find that all three of these, trusses, frames, and machines, are applications of the statics that we've already learned. Okay. We're not going to technically use or learn anything new. We're just going to apply it in specific ways. Okay. That's what we're doing in module 6. So assumptions about simple plane trusses. The bars are connected at their ends to form joints that behave like frictionless pins. Okay. And this should sound familiar to us. We know that there is going to be an X and a Y reaction. Okay. Which we've learned already. We learned that in our previous module 5. All forces acting on a truss are applied at the joints. This is what makes it different than a frame. A frame, we can apply forces or loads mid-span or somewhere along the span. On trusses, it can only be at the joints. Okay, so we'll see that in application. The members and joints are going to lie in a single plane, meaning we're only dealing with the X and Y planes. We're not dealing with the Z. And because it's a truss and it supports loads, we don't want it moving around. So that means that we're in equilibrium. We're in static equilibrium. So some of our forces, some of our moments are all going to equal 0, just like they did in chapter 5. Okay. Now, analysis of truss involves finding the magnitude of the force in each one of the members and whether it is in tension or compression. If it's in tension, we are going to find that the force along that member is going to pull away from the joint. All right. We'll be applying this and looking at this extensively in our examples. If we are in compression for that member, it's going to be pushing on the actual joint. So the direction of that arrowhead is going to let us know if we're in tension or compression. Okay. Now, method of joints. There is a process that we're going to go through here. Okay. So number one, when we have a truss, we are going to first draw the free body diagram as a whole together truss. Okay. And we are going to then determine the reactions at the supports. This is module 5 stuff. This is module 5 right there, 1 and 2. I've been preparing for you for this. Okay. This is the first step that we're going to do. Module 5, determining the reactions at the supports using our equations of equilibrium. Then once we have all of the forces identified, applied loads and reactions at the supports, then we're going to go to step number 3, and we're going to break into the joints and start where we know the most. Now, that might not make a whole lot of sense right now because you don't know much about trusses, but as we work through, I'll talk you through why we would start in a certain place and not in another. Then once we look at each one of these joints, then in each one of the joints, we're going to include any applied loads and all reactions at the supports that are applicable for that joint. Then we're going to draw the forces along the lines or of the members. Then we're going to use the equations of equilibrium. These are concurrent forces because we have the forces only applied at the joints. Those are acting kind of like that point where there's an intersection point for the members, the forces in the members, as well as the applied loads and reactions. Now, the next one here, if a force pulls or if a force is pointing towards a joint, is this tension or compression? You can look back. It's on the previous page. Tension or compression? What would I put in this blank at D? Compression. I would put compression in there. Yes. So when I have a force along a member and it's pointing at the joint, I'm going to say that's in compression. That means that when we're pulling away, that's going to be in tension. Now, why would I want to know that? Any idea? Why would I want to know if it's in tension or compression? Virtually, if you want to either put in the chat box or say verbally. Any ideas? What's the next class that you guys are going to take after this one? Do you know what the prereq, what this is a prereq for? Not kinematics.
Mechanics.
Nope, not dynamic. Well, it is, but that's later on. Solid mechanics. Yeah, solid mechanics is the study of the strength of materials. Okay. All materials have mechanical properties, and certain materials are better at things than others. So for instance, if we know that a member is in compression, it might point to the fact that we're going to use steel for that. Or if it's in tension, it might be steel as well, but maybe a certain grade. Materials like, for instance, concrete. They're great at compression all day long, but as soon as you start trying to pull on them, they don't do so great. All right. They start to crumble apart. We see that in Wisconsin in our roads, right? So that's why at the statics level, we aren't going to do anything with tension or compression, but we are going to say if it's in tension or compression, you would finish that problem if you would in strength of materials. So all of the statics that we're learning here, you are going to continue to be, it's going to be the first step in the strength of material problems that you'll end up doing later on. It's kind of like you finish them up there, if you would, okay? But we've got to be really good at statics in order to do that. So we're specifying tension or compression, and later on, although we won't be doing it in this class, it would become important for how much and the type of material that we would be putting in place to safely support those loads, okay? And then once we have that for the particular joint, we're then going to move to a new joint and then making sure that all those forces that were determined in tension or compression are in the same orientation on the next joint. And then we continue to move around until we get to the last joint, which should equal 0 because we're in equilibrium. So that's what it says here. So it's going to be a lengthy process, all right, because you're going to find out that we have, trusses that have 6, 7 joints. So you end up doing these problems, or you end up, working on each one of the joints separately. But we're going to go through and we're going to do 2 really good examples here this evening. And then I'm going to also then pair it with MD Solids, that software that we touched on or talked about earlier, and how we can use that to aid us, or at least give us a check for the work that we're doing, in a computer program format. So we are going to start our first application of trusses with example 6.2, and this is on page 108 in our handouts, okay? So I'm gonna, here, example 6.2 is on page 108 here. It's at the top. I'm gonna zoom in on the original truss illustration here. So it says here, shown in this figure is a simple plain truss. So when we say simple plain truss, remember, that means that the assumptions that we talked about on our first page are going to be in play. So the assumptions, zoom out here a little bit, are right here, these 4. The bars are connected at their ends to form joints that are going to behave like frictionless pins. All the forces acting on the truss are going to be applied at the joints, not mid-span. Then it becomes a frame, which is different. The members, joints, and loads are all in the same plane, the XY plane, and we're always dealing with equilibrium, okay? So as we look here, it's a plain truss. Those are the assumptions that we have. So you can see that the 2 applied loads that we have for this particular problem, the 4.5 kilonewtons and the 13.5 kilonewtons, are at a joint, okay? Now you can see the truss forms a number of triangles here. And at the ends, we have supports. On our left-hand side, tell me what type of support this looks like. Starts with a P. Okay. It's a pin support, yes. On the right-hand side, what does it look like? I'm going to zoom in. There's little circles at the bottom here. That's going to be a roller. That's represented as a roller. Okay, so it looks maybe a little bit different, but that's another way that you can show it. So this is going to be a roller. This is going to be a frictionless pin on the left-hand side. Now, as we look at solving these problems, again, there is a process that we go through, and that's why I have this here. The first 2 are going to be module 5 stuff. So this should be very fresh and familiar to us. We're going to draw a free body diagram of the whole truss together. Okay. Don't forget your convention, and we're going to determine the reactions at the supports as this truss is together. So first things first, we are going to draw our free body diagram in the space that we have provided here for our guided notes. So that's what I'm going to do here. What I'm going to do is I'm going to do it on the side. In case you don't have the PDF up, I'm going to put on the screen here. This is our truss, and what we want to do is we want to just basically draw the outside of the rectangle with all of the members on the inside, add our applied loads, the dimensions that we see here, and then represent A and D with a pin at A and a roller at D. And then I'll pull mine up and after I have mine all drawn out here. Make it nice and big, not kidding. We're going to be adding, information, and it's a good idea to have enough room. It's always better to have more room than you need. Don't forget your convention. And the convention holds for the entire problem. So you only have to put it on once. Remember to put your reactions at A and D. Assume a direction. For a pin, you've got an X and a Y, right? For a roller, you're going to have one that is going to be perpendicular to the surface it's riding on. And then don't forget your dimensions. Go out here. This is what my free body diagram looks like. So now our first step here, then, once we get our free body diagram in place, we are going to solve for the reactions at the supports. The two supports were the pin and the roller. So we're going to be finding what are the values of AX, AY, and, oopsie, I forgot to label this one, DY. Okay. So if you wanted to go ahead, you're like, I'm totally an equilibrium expert. I can totally do that. Go ahead. But I'll just wait for everybody to get this drawn. Don't want to move ahead too quickly, and then we'll get started in about 30 seconds. So our second step here is going to be equations of equilibrium to solve for the reactions at the support. So again, I'm keeping this truss all together. So I need to find AX, AY, and DY. I'm going to start with sum my forces in the X direction equal to 0. Okay. So anything that's in the, in the horizontal direction. So I've got a negative AX, that's the direction I chose. And then I've got a positive 4.5 kilonewtons. Okay. That's the sum of the forces in the X on the left-hand side here. And I'm going to set that equal to 0. So now I only have one unknown to solve for here, which is my AX. I'm going to move the 4.5 to the other side. So I have a negative AX is equal to a negative 4.5 kilonewtons. I just moved the 4.5. I don't know. I like to keep my variable on the left-hand side. You could definitely move your variable to the right-hand side and then make it positive. But because we have two negatives on either side, it becomes positive. So that means that the AX direction that I chose going to the left was correct. Remember, positive as my final answer confirms the direction that I chose to put my variable in. So my AX here is 4.5 kilonewtons. Okay. Now, again, we've been doing this enough that as I look at if I want to sum my forces in the Y, I can see that I have two unknowns, right? So I'm not going to start with my Y, or I'm not going to use my Y next. I'm going to sum my moments around either D or A to solve for the other variables. So I am going to do my sum my moments. I'm going to use A just because on the left-hand side, I end up using it a lot and starting there, but you certainly could go around D. So I'm going to start at A here. And I'm going to look at each one of the individual forces. So I've got my 13.5 I'm going to start with, and that's kilonewtons times perpendicular distance of 3 meters. Okay. And it is going to rotate clockwise. So according to my convention, that is going to be negative out front. The next one that I have is going to be my dy. My dy is pointing up the way that I assumed the direction. So it is going to be multiplied by 9 meters. And its rotation is clockwise or counterclockwise. So it's going to be a positive out front.
Shouldn't that be a 4 meters for the first one?
No.
It's oh, never mind. All right, I'm
Yep,
sorry.
yep, you see it? Yep. So it's going to be
6 meters.
6 over here. When I go up to the 4.5, that will be a 4. So now we're going to go up to the 4.5. And it is going to cause a rotation, right? That's going to be in a clockwise direction. So it's going to be 4.5 kilonewtons. And its perpendicular distance, these sometimes aren't as easy, but you can move it, remember, along its line of action. I like to get it in line. So when I go up here, this is my perpendicular distance, which would be the 4 meters, okay? So 4 meters is going to be my distance for that one, and it is going to rotate clockwise, so a minus out front. Those are all the offset forces causing rotation. So that's my sum of my moments around A equal to 0. And as I look at my equation, my only unknown here is dy. So go ahead and solve for dy. Oh, did I? Oh, yeah, I meant to say 6. Yeah, 13.5 times 6. I'm so sorry. Thank you. Thank you, Camden. Talking and writing. I'm pretty good at it. I haven't perfected it yet. Thank you. I think I even said 6. I think I wrote 3. I feel like I did. I don't know. I have a recording. We can check. All right. So go ahead and solve for your dy here. So once you get this done, your dy should come out to be 9 kilonewtons. Okay. And you can kind of see negative 99 here when you combine these two, plus 9 meters times dy is equal to 0. Moving that 99 to the other side becomes positive. So now we have 2 positives on either side, which is good. Divide by my 9 meters. My meters cancel out here. I'm left with kilonewtons, which makes sense for a force. Okay. So 11 kilonewtons is going to be my dy. So we can say 11 kilonewtons here. We've got one more. We've got ay to solve for. And that we're going to use sum the forces in the y equals 0. I'm going to sneak it in on here. I think I'm going to put it up over here. I hate doing this, but rather than going to the next page and having to flip back and forth, I'm just going to put it right here. So sum my forces in the y equals 0. I have my positive ay minus 13.5 kilonewtons and a positive 11 kilonewtons, which is our dy, equal to 0. My only unknown here is going to be my ay. So my ay looks like it's going to be negative 2.5 kilonewtons on this side. Move it to the other side. It's going to be a positive 2.5 kilonewtons, right? That means that we assumed the correct direction. So ay is 2.5. Any questions on that? That's all review for us, right? We have done this a number of times, right? So piece of cake. So that's module 5 stuff. Now what we're going to do, if we go back up to our procedure here, we are going to break into each one of the joints. So now we're going to look at the individual joints, and the joints that we have here are A, B, C, D, E, and F. We're going to look at each one of those separately. And this is where there's going to be more, steps that are going to be involved. Now, it says here that we're going to start where we know the most. Now, at this point, you don't know where you know the most, all right? But I'm going to tell you where we know the most. We know the most either at A or at D. If we start, like, let's say at an F, there are no forces, there are no reactions. It's like we're going to look at it and be like, we don't know anything. So we want to start where we see some forces or some action going on, if you would. So we're going to start at joint A. All right. Now, this is called the method of joints because we are going to look at each one of these joints separately. So first thing we're going to do, we're going to label this joint A. Okay. Now we're going to draw the joint. So I'm going to just draw a point like this. This is going to be where A comes together. Then what we're going to do is we're going to look at the truss. As we look at the truss, there are 2 members coming into it. So AF, this is going to be line AF, and this is going to be line AB. So we're going to draw those lines to represent each one of those members. So we're going to draw A to B and A to F. Now, remember what we said on trusses, the forces are going to be along their members. So this represents the vector, if you would, for the member. We're going to put arrowheads on in a little bit, but we're just going to label this AB and AF, okay? And that's going to be the label for the force, the variable for the force. So it's just line AF, line AB, but it's going to be represented by a vector. Now, the other thing that we have going on at A, we have the reaction forces. We're going to keep the reaction forces in the exact orientation that we have here. So we have 2.5 in the Y going up, 2.5 kilonewtons, and then we have 4.5 going to the left for that AX. So I'm not even going to label them AX or AY anymore. They are just going to simply be 4.5 kilonewtons going to the left in the X direction and going up 2.5 kilonewtons. And then this is joint A. So this represents what we already know. Now what we want to do is we want to add in the direction of the forces along the members.
Don't you mean 2 point?
Yep, 2.5.
Oh, don't you mean 2 kilonewtons? Oh, my bad.
No, that's okay. Yep. No, we got 2.5 at Y. Yeah, that's okay. Yep. Okay. So what we want to do is we want to put these along each one of these members. Now, as we look, this force is going to be going either up and to the right or down and to the left. So as you can imagine, we're going to be breaking it into its X and Y components. So instead of putting the X and Y components right at the application of the joint, because that's actually where they're going to be, we're going to back it up a little bit so it doesn't get too cluttered. And you're going to notice I'm going to put my X and Y components just back a little bit. The true application, they will be at point A, but this helps us to just kind of separate them and have a little bit of space to write things. So this is going to be ABX and this is going to be ABY. Now, directions. As we look at the applied loads, you'll notice that we have the one Y direction. And if we look at the other member is only horizontal, okay? It does not have a Y component. This one has a Y component. And if we already know at joint A that we have a force at that support going up, to keep this in equilibrium, which way am I going to have ABY? Keep it in equilibrium to balance it out. It's going to go up or down. If I have this one going up, this one's going to go down. Exactly. Now, if my Y component of member AB is going down, do you see how AB has to go down and to the left? because its Y component is going down. And if this is going down and to the left, my X component also has to go to the left. If I didn't have these forces at A, like let's say I would have been starting here at F. See how there's nothing to even go on? That's why you want to start your truss where you know something. And that's why where your supports are is the natural place to start, either on one end or the other. So now we have to put a direction for our force AF. You'll notice that we have the 4.5 going to the left, and we have established, we're pretty sure that ABX is going to go to the left. So that means to balance this and keep us in equilibrium, AF needs to go to the right. Okay. Now, don't get too caught up in getting it right the first time, because just like we had in our module 5, we will find out if we were right or not if we get a positive number as the final answer. Okay, that rule is still going to apply here. Okay, so if you're unsure or there's not enough information to decide on a direction, just put a direction and include it, and then you'll know if you were right or not. Okay, so now as we look here, we have, if you would, two main unknowns, but we've got a Y and an X for the AB. So we've got 1, 2, 3 unknowns that we need to solve for. So we're going to do our equations of equilibrium. Now, as we look here, though, to determine the values for AB, we have the X and the Y components, and AB is at an angle. So we're going to need to find the angle that this is at. Okay. Now, if we look back at our truss, that angle theta is going to be here, right? And these truss members, you're going to notice they're all the same size triangle. So if theta is here, we're going to notice that theta is here, theta is here, and theta is here. Okay. So it's going to be an angle that we're going to need. So we need to solve for theta. You'll notice that theta, the placement of it, the side opposite is 4, and the side adjacent is 3. Okay, so go ahead and solve for theta. So you should have gotten 53.13 degrees, right? Okay. Now we'll be using that to solve for the, or put the X and the Y components in terms of their hypotenuse. So that's the next work that we're going to do. We're going to find the values for ABY and ABX. So I'm going to start with ABX. It's going to be equal to, as we look at this angle, this is the same angle right here. This is the side adjacent, right? So we would use the cosine of 53.13 times AB, the hypotenuse, because we want to know what is the force in the member. So ABX, so if we take 53.13 and do the cosine, that's going to be 0.6 times AB. Okay, so when we are going to be putting the ABX in place in our equations, we're instead going to substitute 0.6 AB. Same thing for the ABY. This is going to be the sine then of 53.13 times AB. So ABY should be 0.8, right? 0.8 AB. If you hold the whole decimal, it's going to be exactly 0.8. If you round, then it'll be 0.799999, but you want to put it to 0.8. Okay. So now we're ready. We have these in their components. We're ready to use our equations of equilibrium, right? Now, because this is a concurrent force system, all of the forces come together at that common point. We're not going to be using moments, because if we put our finger on M, All of these are going around. I have these offset. These are not offset. They are going through the point. It's just to show the components offset so that we can label them nicely. So we're only going to use some of the forces in the x equals 0, some of the forces in the y equals 0. Okay. So down here below, I'm going to do my sum of my forces in the x equals 0. So I'll notice that I have a negative 4.5 kilonewtons. I have a positive AF, right? And then I have a negative ABX 0.6 AB, okay? Equal to 0. So the left-hand side here is my sum of my forces in the x, equal to 0 is the end of the equation. I can put my 4.5 on the other side, so I can say AF minus 0.6 AB is equal to 4.5 kilonewtons, but I've got two unknowns here, right? So algebraically, I can't solve, but I've got my other equation of equilibrium to see if that helps me out. So over here, I'm going to do my sum of my forces in the y equals 0. And I'm going to look, I've got a positive 2.5 kilonewtons, right? And I've just got the negative ABY, which I'm going to substitute 0.8 AB. Okay. Those are the only forces in the y direction, so I can set that equal to 0. And now I can solve for AB here, right? So I'm going to move my 2.5 to the other side. So it's going to be negative 0.8 AB is equal to negative 2.5 kilonewtons. Okay. This is where watch your signs. If you get one negative sign wrong, especially in the beginning, your whole problem is going to be wrong. Sorry, it's just how it goes. So now we can see that we can make these both positive, which is good because then we assume the right direction. And then we can divide both sides by the 0.8. And our AB, what do we get? 3.125. Yeah, that sounds good. So 3.125. I'm going to hold that third decimal place, and that's kilonewtons. That's what's left over here. Make sure you're showing your units in. This ended up as a positive value, so the direction we assumed going down and to the left is correct. Okay. Now, this is the force in the member. Okay. If you recall from our process here, we have to identify if this is in tension or compression. It's in compression if that force is pointing at the joint. It's in tension if it's pulling away. So if we look at AB, because we just got its magnitude, and we look up here, it's pointing at the joint. So that means that this is in compression. You're going to put a C in back of the value. So not only do you have to have the magnitude of the force in the member, you have to let me know, is it in tension or compression? And then that you put a box around, because that's the first answer that we have for this. We need to determine all the forces in each one of the members. Okay. So we got one done. Got a couple more to go. So now that we know what AB is, we can substitute the 3.125 up in here to solve for AF. So go ahead and do that. Hold the 3 decimal places, 6.375, resist the urge to round it to 6.38, okay? Hold that extra decimal place. And that's going to be kilonewtons. Now, we need to determine and identify if this is in tension or compression. Notice that AF is pulling away from the joint, so this is going to be in tension. So for each one of your answers, for the force in the member, you have the magnitude and you have the direction. All right. Then now we have each one of our unknowns. We had 2 unknowns going into this problem, or the 2 unknowns in those 2 members, and we got each one of those. So now we can move to our next joint. Okay. Go down here. I'm going to try to get it underneath. So if we look back at our illustration, we did joint A, that one's done. the next logical place to go is to go to some place that is attached to it. So we already determined the force in AB. So either going up to B or going over to F. I'm going to go up to B. Okay. So we're going to now do that very same process. We're going to look at joint B. Okay. So B is kind of like up here-ish, right? And now I like to draw just the members coming from it. And then we're going to be adding in anything that we know. So as we look at joint B, there are 3 members attached to it. The member going down to A, which we already called AB. So we want to continue to call that force the same thing. Don't call this BA, because up here we solve for it as AB. We're going to continue to call it AB, whatever you call it first. And I usually tend to take my first, the point, and then whatever the letter is going to be the first time that I encounter it. Then I have the member over to C, so I'm calling that BC, and then I have the member going down to F. One of these members we know, and we know it from the previous joint. We know what AB is. We know that AB is 3.125 kilonewtons. Okay. We also know that it was in compression, right? So it attaches to both joints, right? This one member attaches to both joints. So if it is in compression on A, it is also in compression on B. So you might say we kind of switch the direction of it, but we're consistent with the application of the member on the joints. It's pushing on the joints in compression, okay? So do not show it going down into the left. It was down into the left, pushing or in compression on A. It's joined both to A and B. So now we have to be pushing or in compression on B as well, right? And then it has, just like we know, it's going to have its X and its Y components. So we're going to be putting those in place. The X is going to point to the left. The Y is going to point up, because now we have the AB going up and to the right. So that means our X has to go to the right and our Y has to go up. So this is going to be ABX, and this is going to be ABY. Now we want to put their values there, all right? And we know that the X component up here at AB was 0.6 times AB. So we can take the 0.3125, which was the magnitude of AB, multiply it by 0.6, and that is going to be 0.1875 kilonewtons for that X component, pointing to the right. The Y component is going to be 0.8 times 3.125. So if we take 3.125, 0.8 times, we're going to get 2.5. And that's for the Y component. Okay. Now, why do I want to do that? Well, as you know, we're going to be summing our forces in the X and Y. So might as well get them there right away so that we don't have to end up calculating them later on. Okay. All right. Now, that's what we know. We have to now then assign our directions for the 2 members that we need the values for. So if we look at what we know, we have an X component going to the right here. We have an X member right here. So to keep this in equilibrium, it kind of makes sense to show BC pointing towards the left or pushing on B. The Y component of AB, which we knew, right, and we calculated, is going up 2.5. So it makes sense that BF is going to pull down as well. Okay, keep it in equilibrium. So we just need to solve for the forces BC and BF. So we're going to use our equations of equilibrium. We're going to sum our forces in the X equals 0. So I've got a positive 0.1875 kilonewtons, and I've got a negative BC. Set that equal to 0. I've only got one unknown here, so my negative BC is going to be equal to a negative 0.1875 kilonewtons. They both become positive. So that means I assumed the correct direction here for BC, and its magnitude is 0.1875. That's not correct. Oh, is it, oh yeah. I must have copied that wrong. 1.875. If you notice that ever, maybe you didn't notice it, let me know right away. I'm so sorry. This is 1.875. Yeah. There we go. It wanted my calculator okay, but I must have transposed it when I put it here. So 1.875 in the X. So the magnitude of BC is 1.875 here. Now, we assumed it going to the left. We ended up with a positive value as our final answer, which means that we assumed the correct direction. So don't change this direction. This is going in a negative direction confirmed by the positive final answer. So since we have the magnitude of BC, which is one of our members, we now have to add, is it in tension or compression? It's pointing at the joint. Gabrielle says compression. I agree. So we're going to put a C in back of it. And we're going to put a box around because that's one of the forces in our members. Now we have one more unknown here, right? BF. So we're going to sum our forces in the Y direction equal to 0. We have 2.5 going up as the ABY. So this is going to be 2.5 kilonewtons positive. And we have a minus BF equal to 0. Pushing that to the other side, we're going to have a negative BF is equal to a negative 2.5 kilonewton. The negatives become positive, confirming the direction of BF. Its magnitude is 2.5, and is it in tension or compression?
Tension.
Tension. Tyler says tension. You are correct. It's pulling away from the joint. So that means it's in tension. Aren't these fun? So good. Jacob's like, absolutely. I can't wait to do 4 more problems like this.
I think there's two little stuff.
Two little stuff. All right. So we've got 2 of our joints done. Let's look back over here. We did joint A, we did joint B. We have member AB done. We have member AF done. We have member BF done, and we have member BC done. So we're about halfway, right? And we just did 2 joints. So that's exciting. So where do we want to go next? We're gonna go to F?
Yeah.
Should we do F? Yeah, go ahead. Let's do F. So we're gonna start it just like we did the other ones. Okay. It's gonna be joint F. Joint F is down. So I'm gonna go like here for F. And I had a member going over to A, right? I have a member going over to, I think that's E, right? Yes. And then I've got a member going up to B and over to C, up and over to C. A lot going on at F. It's a busy joint. So we know this is BF. We know this is AF. This is going to be FE, and this is going to be FC. We only worry about what's coming together at F. Okay, we're not gonna put in BC. Okay, that was on joint B, and then we'll see it again on joint C, but only on F here. Now we have to look back. What do we know? So if we look back at joint B, this is where we had BF, 2.5 kilonewtons in tension. So it has to be 2.5 kilonewtons in tension on F. So that means that it's going to pull away from F, right? BF. And this is equal to, I'm actually going to move my BF over. This is going to be 2.5 kilonewtons BF is equal, right? You don't have to put tension here because the direction of your force is in tension, okay? So it has to be pulling away. AF, we did calculate already back on joint A. So that was in tension, 6.375 kilonewtons, okay? So it was in tension pulling away from A. So that means it's going to be in tension pulling away from F. And it was 6.875 kilonewtons. All right. Now we've got two unknown members, right? We have to add our arrowheads to here. So I'm going to start with FE. I really don't know. We're gonna have an X and a Y component here. So down to the left. So I'm thinking it's gonna go to the right. We'll see. We'll see. I'm gonna pull away. Yeah.
BF is going down. So that's what we determined on joint B.
Let's remember. So this was in tension on B. So it has to be in tension on F. It has to pull away. Pull away, because it's going to be in tension on both joints.
Okay.
Yep. So in essence, you do flip the direction of the vector as we go from one joint to the other, but to be consistent, if it's a compressive member, it's going to push on both joints. If it's a tension member, it's pulling on both joints. And it's connected to both joints, so it not only has to pull on B, it has to pull on F. We'll continue to do that. Yep. Good question. So I'm going to assume FE going to the right. And we know that because FC is at an angle, there's going to be X and Y components, right? So I'm going to have an FCX. I'm going to move this over a little bit, 2.5 kilon. I'll do this. This is why we have a pencil. 2.5 kilonewtons is going to go there. And then this is FCY. Now, our Y component for BF is going up, right? Pulling away from F. So to keep this in equilibrium, this is the only other Y, it's going to go down. That means that FC has to go down, and then this is going to go to the left, okay? To be consistent. For right now, we'll check these directions. If you do them in opposite directions, that's okay, but you have to make sure that your hypotenuse, the FC here, if you say that's going to go down and to the left, that dictates your Y direction and your X direction. If you assign up and to the right, then your Y has to go up and your X has to go to the right, okay? All right, so then now we get to determine the components of each one of these angles. Now, remember this angle right here, as we identified in our original diagram, this angle right here from F up to C, the angle theta, was the same as theta was over at A. So we don't have to recalculate the values. That means that our X's are going to be 0.6 and our Y's are going to be 0.8. It's the same angle in each one of these, okay? So we can sum our forces in let's do the Y direction first, because there's fewer Y's. We have a positive 2.5 kilonewtons, it's going up, a minus FCY. That is going to be 0.8, it's the Y component, 0.8 times FC. You see that? So this right here is FCY. So the Y component is a 0.8 like it was back on joint A here, because it was the sine of 53.13 degrees, okay? So this right here is FCY. Those are the only two in the Y direction. We can set that equal to 0. So our only unknown is FC. I'm going to move my 2.5 to the other side. So negative 0.8 FC is equal to negative 2.5 kilonewtons. Both become positive. Divide both sides by 0.8. And I'm going to have FC equal to 3.125. It sounds familiar. You had that number before, right? If you end up getting repeat numbers as you go through a truss, you know you're doing it correctly. Just so you know. Not that they all have to repeat or be used in different places, but knowing that we got a 3.125 here and we had a 3.125 on the first joint, that means that's good. Okay, am I done with the magnitude at FC? I can move on. I didn't tell you if it was tension or compression. We have to add that. Absolutely, Jesse. So what is it? Tension or compression? Compression, because it's pointing at the joint. So make sure you put your C here. And then we can put our box around, right? Okay, go ahead and solve for FE. Okay, go ahead and solve for FE. See how you would approach that. AF is 6.375. That's me. Sorry. If you guys, hopefully you caught that on your own, but I wrote it as 6.875. So AF is 6.375. I'm not good at this tonight. Did you guys ever have those days? I guess this is my night. Plus. There we go. That's the number I need. You get 8.25 kilonewtons. Plus FE. Took me a while to get there. Okay, tension or compression? FE is pulling away. So tension or compression?
Tension.
Tension, yes, good. Good. Box around, because that's one of our knowns. So if we go back to our truss, we now know FC and FE. Where do you want to go? Do you want to go to C or do you want to go to E? Which one looks more fun?
E should be pretty easy.
D is going to be amazingly easy.
E.
You want to go to E? Sure, let's go to E. Okay. You guys get to start this one on your own. Join E. See what you come up with. I don't know if I'm going to fit this all on here, but that's okay. Don't forget your applied load of 13.5 pulling down at E, okay? You have to include that. Do not switch that direction. Applied loads and reactions to supports stay in their actual orientation. They're like applied loads, they're external loads. FE is going to be in tension, pulling away or pointing to the left. 8.25 kilonewtons, okay? And then I set my directions for EC and ED so that they would balance out the loads that we knew, okay, from the previous joints and the applied load that we see here. So then you can go ahead and sum your forces, X and Y equal to 0, to solve for those unknowns. That's 3 times. I think that means I'm done for the night. I don't know if it's my eyes aren't working or if I'm too preoccupied. I think I had too much caffeine today. Which I think I kind of did. All right. So you should get the force from joint E to D to be 8.25 in tension. And your E to C, 13.5 in tension going up from E. All right. Any questions? Did that work out okay for you guys? Yeah, okay, good. Now we get to go to another joint. I know, so good. So if we look back, let's see what we do know. We know E to C, we know D to E. We could go to D or C. I'm going to say we're going to go to C. And we're going to save D for the end, okay? So we've got 2 more joints to do. So we're going to go up to joint C. So go ahead. Am I going to fit it on here? I hope so. Ugh. I'm going to start a new piece of paper. You might be able to fit yours, but I don't think I'm going to. So my next one is going to be joint C. Don't forget the applied load of 4.5 going to the right. And you've got to look back at your previous joints. BC was in tension, and it was a value of 1.875 on B. So it is going to be in tension, pulling away from C, 1.875 kilonewtons. Okay. We had F to C, FC. We've got to go back to joint F. This was FC. It was in compression, 3.125. So that means it's going to be in compression on C as well. Okay. 3.125 kilonewtons. It then is going to have an X and a Y component going up and to the right. And then each of those magnitudes are going to be multiplied by 0.6 and 0.8. 0.6 for the, make sure the X component, yes, 0.6 for the X, 0.8 for the Y. E or E, actually EC, right? That's what we had from the previous. EC was in tension, its magnitude 13.5 kilonewtons. It is in tension off of E, so it has to be in tension pulling away from C. And that's going to be equal to 13.5 kilonewtons. That's the one coming down right here. Okay. So our only unknown is C to D. Okay. Now that's at an angle, so it's going to have X and Y components. I'm going to put that this way and that way. And I don't know, we've got an up, we've got a down, we've got more down than up, right? So it would seem that our Y should go up, sorry, Y should go up. So this is going to be our CDY. This is going up. That means that CD is going to go up and to the left. So it's going to have an X component then. That's going to go to the left. That's how I'm going to assume it for right now, but we'll see how it all works out. Looks like it's going to be okay. So our only unknown here is CD, right? So we can sum our forces in the X or Y. It doesn't really matter. Or before we start doing that, are there any questions on the diagram? Drew?
Can you just explain really quick, like, because I see that FC and CD, they're both pointing up to the joint.
How did I do? Why did I do that? So, oh, go ahead.
Like, they're middle points, you know what I mean? Like FCX and FCY, and then CDX, CDY, why are they going to the chart?
FCX and FCY, because FC is going up and to the right. So that means that the X component of that force is going to go to the right and the Y is going to go up. I just drew these lines and then I just put the arrowheads on them. Whether it's coming up from here or going that way, it doesn't matter.
Okay.
It's just the components showing the component directions. Okay. So what Drew was asking was, how come I put the arrowheads going this way? I could have gone from this side and gone that way and that way, but I had the lines drawn that way already. So then I just went up and to the left.
Okay.
Jesse.
Wasn't BC compressing?
Let's look. Was it compressing? BC?
Yeah.
See, that's why I have you guys. Oh, it was. Look at that. BC was in compression. Thank you. Yep. See, that would be bad. I'd be like, why am I not getting it right? Yep. So double check those. Thank you. Any other things I did wrong tonight? That's number 4. On one problem. It's actually quite unusual, but that's okay. All right. So now what are we going to do? Sum our forces in the X and Y to equal to 0 and solve for CD. Okay. So I will do that here. Sum the forces in the X equals 0. Actually, I'm going to do it down below because I think I'll run out of room here. is the correct answer. Got this one right. So you should get 13.75 for CD. So we've got 1.875 going to the right BX, that's going to be positive. 1.875 FCX going to the right, positive, and 4.5 kilonewtons applied load on the top going to the right, and then minus CDX, it's the only one going back to the left, equal to 0. Combining those, you get 8.25 minus, this is the X component of CD, so it's going to be 0.6 times CD equal to 0. So then putting the 8.25 to their side, two negatives become positive, divide by 0.6, you get 13.75 kilonewtons. That is the answer. Now, as we look here, we have CD, we end up with a positive value, meaning we assumed the correct direction. It is pointing towards our joint. So it is in compression or tension? Compression, yep. So C, it's going to be behind with a box around. Okay. Any questions on that one? How did that go? You got the same answer. We're in good shape. All right. So we've got one more joint, and this joint is going to confirm everything for us that we did it correctly. So if we go here, we just determined our CD. So we're going to now finish up by doing joint D. You might be like, well, why are we going to do that? There are no unknowns. This confirms that we did everything correctly because it should all come out to 0 at this point. Okay. So we are going to do our one last joint. So this is going to be joint D. Okay. I'm going to start it here. So joint D goes back up to C, goes back over to E, and then we have one reaction. Remember, this was the reaction from the roller. We put that in the same orientation. It was 11 kilonewtons going up. Okay. This was CD, and this was ED. So going back up to joint C, CD was in compression, pushing on. So it's going to be in compression on D. Okay. It's going to have its X and Y components. Okay. Here's my Y and my X. So my X is going to go to the right. My Y is going to go down. Okay. We know CD to be 13.5 kilonewtons. And we can calculate those separately. I'll put it over here. I don't have a ton of room. And then our force E to D, we go back to joint E. It's right here. It's in tension, pulling away, 8.25. So we're going to show it to the left, pulling away from D, 8.25 kilonewtons. So now we're going to sum our forces in the X equals 0. So there's nothing to add here. This is all known at this point on our last joint. It will be all known. So if we look at the X direction, we've got a negative 8.25 kilonewtons for member E to D, plus our CDX is equal to 0. Now our CDX, we know that CD was 13.75. We would multiply it by 0.6. So you would have a negative 8.25 kilonewtons plus 0.6 times 13.75 kilonewtons, right? So this is CD times 0.6 equal to 0. So if we take 0.6 and we multiply by 13.75, what do we get? 8.25. So we have a negative 8.25 kilonewtons plus 8.25 kilonewtons equals to 0. 0 equals 0. That is a good thing. Okay. Brooke. 13 points. Holy buckets. Yeah, it's 13.75. The next one's gonna go back.
Yeah, I think that's.
We should go home. Kelly's having problems here, but you know what? You guys are picking up on it. So be watching. Keep your eyes peeled. Yeah, I had it right here. I didn't have it right there. Oh my goodness. All right.
Almost lecture for almost 2 hours already.
I have. Yeah, I have. Sum of our forces in the y equal to 0. I don't make many usually though. That's why I'm kind of off tonight. So now we're going to look at our y direction. We have a positive 11 kilonewtons going up, and we have a negative CDY, okay, equal to 0. CD is up here. It is 13.75, as Brooke pointed out, absolutely, and we would multiply it by 0.8. So we're going to have a positive 11 kilonewtons minus 0.8 times 13.75 kilonewtons is equal to 0. 0.8 times 13.75, what do we get? We get 11. So 11 kilonewtons minus 11 kilonewtons is equal to 0. 0 equals 0. And you can even end, this is how I like to end this, with a nice little smiley face because it all worked out, even though Kelly was losing it a little bit along the way there. You guys get a discount, money back for tonight. All right. So any questions?
That. We'll see how they go.
What was that?
We'll tell the school that. We'll see how they go.
Ooh, okay. All right. So any questions on this one? This was our first. So you can see that the process for our trusses was, we'll kind of go back. Yes, these are pages here. We start by keeping our truss together. We solve for the reactions at the supports, the pin and our roller. That then rounds out all of our applied loads, okay? Then what we do is we start looking at each one of the joints individually to solve for the forces in the member and identify each one if they're in tension or compression. As we move from joint to joint, we make sure that, for instance, with A and B connected here, if it was in compression on A, it'll be compression on the other joint. So it's going to point towards. So at B, AB is pointing towards. So in essence, you can maybe say you switch the direction from joint to joint, but you keep the application consistent. If it's compression on one, it'll be compression on the other. If it's in tension, pulling away on one of the points that it is connected to, then it's also going to pull away at the other joint. So if we go to F here, AF is pulling away there. Okay, so tension on both of them. So as you move around, make sure that you identify the magnitude of the force and if it's in tension or compression. Okay, and then when you get to the end, like we did here, your last joint should end with 0 in equilibrium. Now, you might be like, there must be a computer program that does this for us, right? Well, that's MD Solids. That's what we were talking about. So I want to do a quick demonstration of MD Solids to show you how to use it. And then we'll be able to apply it on our homework problems as well. So what I'm going to do is I'm going to go back to our original truss. Okay. The original truss problem. Here it is. Right here. So this example, 6.2, we're going to represent this truss in MD Solids. Now, some of you might have downloaded it already. That's great. I'm just going to show you a demonstration. So what I'd like for you to do is just kind of put eyes up here, and I'm going to walk through how to use MD Solids to show how to solve for these reactions in the supports. So I've already, see, I just got to move this little thing here. I have already downloaded and have MD Solids available. So sorry, I've got like a million windows here. MD Solids is going to be the icon that you see here. So once you download it or you open up that setup file, you register, you're going to have this icon on your desktop. So I'm gonna click on the MD solids and it's gonna open up, okay? I'll maximize it here on my screen. And now what you're going to have is you're gonna have a menu of items to choose from. Where we're gonna go here, I guess is obvious, we're gonna go into the trusses little square, okay? So I'm gonna click on the trusses, and what you end up finding here is that you have kind of this place, not really to draw, but to start specifying. Now, over on the left-hand side here, you want to click the button that says New Truss, okay? So I'm going to click that button, and you're going to get this menu is going to appear. This sets the definition of the grid, okay? So the first one says horizontal spacing interval. So that means any X distances. So if we look back, oh, it's not going to let me move this. Hold on. I want to look back at my illustration. I can't. My horizontal distance here is 3 meters. So I'm going to put my horizontal increment, and then you're going to say how many spaces. So if we look horizontally along that truss, there was 3 spaces, and you're going to do the up and down arrow to specify that. The vertical spacing then, in our case, it was 1 high and it was 4 meters high. The number of spaces is just 1, okay? So you set that up right here. Now what's going to happen is I'm going to hit OK, and it's going to create this grid. Now, this is not sophisticated CAD business here, okay? This is pretty simplistic, so I'm going to kind of give you a hint on how to do this. So you're going to notice that the box over here says create, and then it has that checked as well as members. So we're going to put our members in our grid here. To do this, I'm going to start, this would be at the bottom here, corresponding to the point A on our truss. I'm going to left click when I get close. It's not going to snap. This is not a CAD program, okay? So I'm going to left click, hold, and then release when I get up to the next or close to the next intersection, okay? Then I'm going to start up on top here. I'm going to go down and release. The order you do this in, and again, you're going to hold and then release when you get to the intersection. And you're going to notice that each one of these members starts going in, okay? And now this is my truss. It automatically calculated the angles for me. This is 3 inches wide. This is, or 3 units wide. We really didn't specify units. And then 4 tall, okay? And how many grid spots we did? We did 1, 2, 3, like spaces horizontally. We did 1 space vertically. Okay, that's when we filled up that little table. Now we have our members in place. The next thing we're going to do is we're going to click on supports. Okay, click on supports. Now it tells you here, you know, to click and then drag left or right direction for the direction that you're going to go in. The direction of the supports isn't as critical, but I'll show you how to do it. So if they don't end up in the right orientation, sometimes it's not a big deal, especially for the pins. So the first one I'm going to do is down here at A. I'm going to left click and pull down, drag and release. And the first thing it does is it's going to assume a roller. I'm simply going to left click and I'm going to go to the left, and now it's going to make it a pin. You'll notice that the pin is oriented, if you would, vertical. Remember, a pin is an X and a Y support. It really doesn't matter if the wall is vertical or horizontal because it's going to support in both directions anyway. Now I'm going to go over to the other support, and I'm going to just left click going down and release. And now you'll notice it kind of straightened things out and it put a roller over there. Okay. So now I have my supports in place. I have a pin at A. I have a roller at B. Okay. If you want to change it to a pin or a roller, again, you just left click on it again and you release and it toggles to the next one. The last thing I want to create or add is going to be my loads. So the 2 loads that I have, the first one is up here at the top. I'm going to left click, drag to the right for the direction and release. And now it's going to ask me what the magnitude is, and it's going to be 4.5. Enter. And then the other one that I have is down at E, and it's going to go down, drag, release, and then 13.5 going down. Okay. Don't have to worry about kilonewtons or anything. These are just going to kind of be in generic units, and then you can apply the units that are appropriate for your problem. So now I have my members in place, my supports, and my loads, okay? The next thing that I want to show you is, let's say you put something in wrong and you want to erase it. what you're going to do is you're going to go to erase mode and you're going to pick what you want to erase. So if you want to get rid of a member, you've got to click on the member and then left click on it and then left click on it and it gets rid of that member. Does that make sense? Okay. There is no undo here. No undo. Again, not sophisticated program, very simplistic. So if I want to add that back in, I've got to go back up to create, make sure that I'm on menu, left click, release, and then drag and release if you would. And now it goes back in. Okay. All right. So that's how you can kind of play with it. Now, the next thing we're going to do once we have everything in place, you're going to notice this compute button becomes available to us. That's going to be how we're going to compute the forces in the members. So I'm going to click on compute and look at that. All right. Now, this gives us what the members are. So when we look at our homework, there's going to be one problem you're going to do the manual calculations for, and then you're going to accompany MD solids with it. My suggestion for that problem for you is to run the MD solids first, because that's your answer key. And then that way, when you do the manual solution, you can then check member by member if you did it correctly or not before you get too far along. Does that make sense? Or wait till you get to the last joint. So this is MD solids. Now to print this off, okay, you can go up to File and simply go to Print. It's gonna ask you to make a title of it. So you want to call it Example Problem 6.2. Okay, see, 6.2. And you can say next, and then it's going to ask you what where you want to print to. Okay, I'm going to say print. And then it's going to ask you for font. Don't even change that. Just hit OK. And then it's going to send it to the printer of your choice. Now, two-hand in though, I'm going to say OK. I don't know why I did that. Two-hand in though, yeah, it's not going to remember. You are going to do a screenshot of that, that we saw earlier. Not sure why it gave me an error, but again, it's not the most sophisticated program. In between, let's say you want to do a couple of these trusses at once. What you can do is you can go up here and you can hit new truss and then it'll clear it and you'll be able to start a new truss. Okay. And that's really it. You don't have to necessarily, if you want to, you can file save each one of these if you want to. They don't take long to create. So if you end up not saving it, or you don't be too disappointed because it literally takes 4 minutes to set up. So it's not that big of a deal. Okay. It's a very simple program. It is not sophisticated. So if you're trying to do like fancy window things, and it may not. Okay. But it works great for what we use it for, as you can see. So that is just a little demonstration of MD solids. I'm just going to peek at our homework here really quickly, and then we'll take a break. So if I go to the Module 6 application problems, this is what you're going to be handing in for the homework. You'll notice that problem 6.5, you need to do the manual calculations. So that means that the stuff that we just went through on that example 6.2, you're going to create all of that. Okay. The manual calculations for each one of the joints. Then you're going to run MD solids. You're going to attach MD solids to it. But like I said earlier, MD solids is kind of an answer key for you. I would run the MD solids first, get your values, and then as you're working the manual calculations and you're going to each one of the joints, make sure that the values for each one of your members matches what you're calculating before you go to the next joint. Or if it doesn't, then do the fixes and then work through it. You'll notice then the next two are just MD solids. You don't have to do manual calculations. So manual calculations only for 6.5, but then you've got 2 more trusses that you're going to do on MD solids. And it's just really practicing setting them up. So I picked 2 more for you to run. And those 2 are only going to be the MD solid screenshots. Okay. So 6.5 is a 20-point problem because of the manual calculations. And then the other 2 are 10 points. Okay. So let's take a break. I think that's enough for right now. We'll come back in about 15 minutes. So at 7:35, we will resume and we'll do a little bit more.